In this video, I will show you how to analyze and sketch the graph of this polynomial function using calculus. Our analysis will consist of these 5 steps. Step 1, where's the function undefined? That would tell us any vertical asymptotes if there were any. Step 2, use the first derivative test to determine where the function is increasing or decreasing, and we'll find any extrema, relative max, relative min. Step 3, second derivative test. This will tell us where the function is concave up or concave down, and we can identify the points of inflection. Step 4, the limits at positive or negative infinity will tell us the horizontal or slant asymptote in general. A polynomial function doesn't have these, but it will tell us the end behavior. And step 5, we will find the x and y intercepts. Normally, the first step is to find where the function is undefined, but polynomial functions never have any places where they are undefined. So, of course, that means there will be no vertical asymptotes. The rest of the steps will be easier to do if we first put the function in factored form, so let's do that. I'm noticing that all of the terms have an x in it, so let's take out a common factor of x, which will leave x to the third power minus 12x squared plus 48x minus 64. I briefly considered factoring the part inside of the parentheses by grouping, but pretty quickly I could see that that wasn't going to work out. So we're going to have to actually use synthetic division. So let's take our minds way back. Haven't done this in a while, but the coefficients are 1, negative 12, 48, and negative 64. We leave a space, put a box at the end, and the goal is to get a 0 right here. Inside the box, we put our guesses for possible roots, possible zeros. We usually just start with positive 1. If we could use our calculator, we could use the table feature to immediately jump right to the zeros. But let's assume that we're not allowed to use our calculator. So let's say we try positive 1. We always start by bringing the first number down. And then we multiply. 1 times 1 is 1. This is going to make negative 11. Negative 11 times 1 is negative 11. And that's going to make 37. 37 times 1 would be 37. That's not going to make 0. So we can already see this is not working. So then we would try negative 1. 1 times negative 1 is negative 1. That's negative 13. Multiply, you get positive 13. That's going to be 61. And multiplied times negative 1, that's going to be negative 61. That's not going to make 0. So then we would try positive 2. That wouldn't work. We would try negative 2. That wouldn't work. We don't need to try 3 because we only have to use numbers that are factors of 64. And 3 does not divide evenly into 64. But then finally, we would get to 4. We would try positive 4. And it would work like this. 1 times 4 is 4. So this is going to make negative 8. And then negative 8 times 4 is negative 32. So this is going to be 16. And 16 times 4 is 64. So finally we get our remainder of 0. Let's translate all of this back into a polynomial. So the factor, the 0 of 4 tells us that we have a factor of x minus 4. We will use these 3 numbers as coefficients, so we will have x squared minus 8x plus 16. Don't forget about the x that's in the very front that we factored out as a GCF. That still exists. So far we have this for the factored form of f of x. But of course, we can factor this trinomial a little bit further. So we will have x times x minus 4. But now let's factor the trinomial. So x squared will factor as x times x. 16 factors as 4 times 4. You know, it could have been 2 times 8 as well, or 1 times 16. But looking at the middle term of negative 8, if we let this be negative 4 and negative 4, that will make the middle term of negative 8 that we want. So this is how it is factored. Let's clean this up a little bit. So we can write f of x equals x times x minus 4 to the third power, because it's 3 of those. Now it is time for the first derivative test. Well, this is a product. Let's go ahead and do the product rule, which says first you take the derivative of the first factor, and that's just going to be 1. And you keep the second factor the same, x minus 4 to the third power. And then you add, and you go back again. This time through, we will leave the first factor alone, and we will multiply by the derivative of the second factor. Well, this is going to be the chain rule because we have an outer function and an inner function. So first, the outer function, we will use the power rule. We will use the power rule and bring this 3 to the front and decrease by 1. But then chain rule says you multiply by the derivative of the inner function. Well, okay, the derivative of x minus 4 is just 1, which I didn't really need to write. So this is what I have so far. I have x minus 4 to the third power plus 3x times x minus 4 squared. So notice the common factor of x minus 4. So let's go ahead and factor that out. How many x minus 4s can I pull out? Well, the smaller exponent worth. So I will pull out the x minus 4 squared. That is going to leave behind, well, that's still going to leave one of these. So I'm still going to have an x minus 4. I feel like I should change these parentheses to brackets. So I'm still going to have a single x minus 4 left from this, and I'm still going to have the 3x. But that's it. I can combine like terms in here. These parentheses aren't really doing anything, so x plus 3x is 4x. And we have the minus 4. There is a common factor inside of here, so let's pull out the 4 and I'll put that in the front. So I'm going to have 4 times x minus 4 squared, and that will leave x minus 1. So this is the form of the first derivative that we're going to be using. In order to perform the first derivative test, we need to find the critical numbers, which will be where the first derivative is equal to 0. It normally would also be where the first derivative is undefined, but for a polynomial function, there's none of those. So setting this equal to 0, using the zero product property, we're just going to get x equals 4 from this factor, and we're going to get x equals 1 from this factor. So these are the two critical numbers. we will use these to separate the number line into intervals. So I have separated the number line into intervals using the critical numbers. I'm labeling this side of the number line as f prime to show that any calculations I do on this side of the line will be evaluations of the first derivative. So I need to pick test values. So I think in this interval, I will use 0 as a test value. In this interval, I will use the number 2. And in the last interval, I will use the number 5. So let's start with the 0. That's going to give us 4 times 0 minus 4 squared times 0 minus 1. So that's going to give us, well, 4 is always positive. In fact, this portion is always going to be positive because 4 is positive and then we're squaring something. So that's definitely going to give us a positive. But 0 minus 1 is a negative. So overall, we're going to get a negative value here. That tells us that the function is decreasing during this interval. Now let's go ahead and evaluate at 2. So we're going to have 4 times 2 minus 4 squared times 2 minus 1. Again, this first portion is automatically going to be positive, but 2 minus 1 is also positive, so we have an overall positive value. That tells us that the function is increasing during this interval. Now let's do the 5. So we have 4 times 5 minus 4 squared times 5 minus 1. So this portion is going to be positive always, but 5 minus 1 is also positive. So we're going to have another positive value. So that tells us that the function is still increasing in this interval. All right, guys, it is time for the second derivative test now. I'm going to look at this as one part of the function, and I'm going to look at this as the other part. So when I do my second derivative, I'm going to do the product rule. The product rule says first, take the derivative of the first factor. So using the power rule, that will be 2 times 4 will give me 8 times x minus 4. But I'm going to have to do the chain rule. So that was the outer function that I just did. But I also have to multiply by the derivative of the inner function, except for, wait a minute, the inner function is x minus 4. The derivative of that is just 1. So yeah, don't need to write that. Okay, but you also have to then multiply by the other part unchanged. So I multiply by x minus 1. Then you put a plus. So for the product rule, next you go through again, but this time the first factor remains unchanged. So I'm just going to keep the 4 times x minus 4 squared, and you multiply by the derivative of the second factor. But again, the derivative of this is just 1, which is not doing anything. So there is an expression for the second derivative. Let's see if we can factor this thing. So we have some common factors here. Look at the 8 and look at the 4. There's a common factor of 4, so let's pull that way out in front. But also, we have a common factor of x minus 4. So let's pull that out in front as well. All right, I think I'll use brackets for a minute. So what's left? If I divide this by 4 and x minus 4. So I'm going to get 2 because 8 divided by 4. And the x minus 4 is out here now, so it's gone. But then I still have the x minus 1. Okay, the 4 is already out here, so it's out of there. I pulled out one of the x minus 4s, but there's still another x minus 4 still left. So I'm just going to simplify this down. All right, so I have 4, I have x minus 4. So this is going to be 2x minus 2 plus x minus 4. All right, I guess I can stop using brackets now that I don't have that mixture of parentheses and brackets. So I have 4 times x minus 4. So just combining like terms, 2x plus x is 3x, and then negative 2 and negative 4 make negative 6. Well, there's one more little step because there's a common factor of 3. So I'm going to pull that common factor of 3 out front. That's going to make this a 12. So I'm going to have f double prime of x is equal to 12. And dividing this by 3 will give me x minus 2. So this is the factored form of the second derivative. So we need to find the values of the possible points of inflection, similar to the critical numbers of the first derivative test. So we will find these possible points of inflection by setting the second derivative equal to 0. Again, normally we would also consider where the second derivative is undefined. Whoops. But the second derivative is still a polynomial, so there will be none of these. So setting this equal to 0, and using the zero product property, we get x equals 4 and x equals 2. All right, so these are the potential locations of points of inflection. We're going to put these numbers on the number line to separate into intervals for the second derivative test. I'm going to mark this side of the line with f double prime to show that any calculations that we do over here will be for the second derivative. So the two numbers that we just found for potential points of inflection were 2 and 4. So I'm going to go ahead and put a white line here at 2 and at 4 to show that these are the numbers that are creating the intervals that we must test. For my test values, I think I will use 0 again in the first interval. So in this interval, I'm going to have to pick a new value. I think I will pick 3 is the obvious choice. And in the final interval, I'm going to use 5 again. So let's start evaluating. So for 0, I'm going to have 12, and then 0 minus 4 times 0 minus 2. So this is going to give me 12 times a negative times a negative. So that's going to be overall a positive value. That tells me that in this interval the function is concave up. So from negative infinity to 2, the function is concave up. Let's evaluate at 3. So we're going to have 12 times 3 minus 4 times 3 minus 2. So that's going to be 12 times a negative times a positive. So this will be an overall negative value, which means that the function will be concave down in this interval. So in the final interval, we will have 12 times 5 minus 4 times 5 minus 2. So we will have 12 times a positive times a positive. So a net value of positive, which tells us that once again in this interval, the function is concave upward. Notice that the function goes from concave up to concave down at the number 2. So that tells us that we have a point of inflection at 2 comma something. Let's go ahead and find the y value that goes with that. So we will evaluate the function, the original function at 2. So this will be 2 times 2 minus 4 to the third power. So that's going to be 2 times negative 2 to the third power. So that's going to be 2 times negative 8. So that will be negative 16. So we have a point of inflection at 2 comma negative 16. We have another point of inflection at 4, where again the function changes concavity, going from concave down to concave up. So we have another point of inflection at 4 comma something. So let's evaluate again. So let's do f at 4, which will be 4 times 4 minus 4 to the third power. So that's going to be 4 times 0 to the third power, which is obviously just going to be 0. So we have another point of inflection at 4 comma 0. Also, notice how the function goes from decreasing to increasing right here at the number 1. That tells us that we have a relative min at the point 1 comma something. Let's go ahead and find that y value. So let's evaluate f at 1, which will be 1 times 1 minus 4 to the third power, which is just going to be negative 3 to the third power, which will be negative 27. Okay. So 1 comma negative 27, that's a big graph, but that's going to be a relative min. It's time to consider the limit of the function as x approaches positive infinity and negative infinity. For a polynomial function, only one term matters, and that is the term of highest degree, the highest power. So you can really just forget about the rest of the function for these purposes. So as x approaches positive infinity, of course, this term will just get bigger and bigger and bigger. So the function will increase without bound. As x approaches negative infinity, well, so remember that these x values will be negative numbers. So x is getting more and more and more negative. However, because this is an even power, they will be turned positive. So in the end, the function, the value of the function will just keep increasing without bound. All right, so positive infinity on both sides. So obviously there's no horizontal asymptote. Polynomial functions don't have horizontal asymptotes, but this tells us that the end behavior is increasing on the left, and it does whatever else it does, but it's also increasing on the right. The last step before graphing is to find the x-intercepts and the y-intercept. We find the x-intercepts by setting the original function equal to 0. So if I set x times x minus 4 to the third power equal to 0, I can just use the zero product property immediately to get x equals 0 and x equals 4, which means that we have two x-intercepts, 0, 0, and 4, 0. For the y-intercept, we evaluate the function at a value of 0. So if I substitute 0 in here, all right, so I'm doing f at 0, that's going to give me 0 times 0 minus 4 to the third power, which is going to just give me 0. So of course the y-intercept is going to be 0, 0. We already knew that the x-intercept was 0, 0, and that's on the y-axis as well. So let's use all of this information to make the graph. So here are the 4 key points that we found. The x and y-intercept 0, 0, a relative min at 1, negative 27, a point of inflection at 2, negative 16, and another point of inflection at 4, 0. Let's look back at our chart and see where the function is increasing and decreasing and where it is concave up versus concave down. So analyzing the chart, we see that the function is decreasing from negative infinity to the relative min, and then it's increasing the rest of the way. So it's just decreasing and then increasing. That's the whole story. Now, as far as concavity, it's going to start off concave up, and then it'll switch to concave down, and then back to concave up again. Let's see if we can do all of that. So the function should be concave up and decreasing until we get to the relative min, where it starts increasing, still concave up, but then at the point of inflection, it switches over and begins to be concave down until it gets to the second point of inflection, where it begins to turn and it will become concave up again. So this is what the function should look like. So one more time, here's our graph. Soak it in and compare that with the real graph right off of Desmos. And as you can see, it's a really good match.